Welcome to the first presentation for the General Motors 4L60E. In this presentation, we'll be introducing this transmission and then talking about the mechanical components and the power flow. This list here has a suggested study schedule, and you're already here at lecture 1. So as you go through this lecture, complete the worksheet. And when you're out at school, go through and explore some of these same parts that we go through. I'm going to have gear sets. I got plenty of gear sets, plenty of the cutaway input drum that you'll see in here and the pieces and parts. So that way, before you even take the transmission apart, you're familiar with the insides of it a little bit. Then you're going to want to go through and watch the overhaul video. I'd like you to do that before you take it apart so that you're going to be familiar with what you're going to be getting yourself into. And then we're going to watch lecture 2, which is basically rebuilding particulars. It's a PowerPoint that I used to have. This would be a relatively quick PowerPoint, and it really kind of hits home some of the things that students run into as far as difficulties and some obstacles that they might run into while they're rebuilding the transmission. A lot of that might be mentioned in this overhaul video, but with lecture 2, there's 20 or so slides with pictures that just basically show some of the mistakes that students have made in the past. And I try to kind of get ahead of those mistakes by pointing them out. So I'd like you to watch that before you, step 4, start working on this lab unit. So at that point, once you've already watched lecture 1, lecture 2, and watched the overhaul video, it'd be a good idea to go through and mount the transmission on the bench and start disassembling it using the overhaul worksheet and a service manual. As you're going through that, because that will likely take you a few days, if not longer, depending on how much time you plan on spending on it. But while you're going through those on your own time, you could also watch lecture 3 and lecture 4. Lecture 3 deals primarily with the electrical side of things, and there is actually a lab worksheet that you'll be able to go through and do some scan tool usage and some electrical measurements and so forth on a vehicle. And lecture 4 is primarily hydraulic power flow, looking at the hydraulic schematics. So that is the gist of the lectures that you get here. All these, the power flow, mechanical, hydraulic, electrical. And once you get all those done, I'm going to want you to go through some of these diagnostic case studies. And the diagnostic case studies kind of pull all those together. You know the names of the parts and the pieces, you know how everything interacts and works with each other. Hopefully you can use that information to diagnose some transmission issues. And when you're all done and the transmission's done, it's all put back together, we've run it on the dyno, you've done your scenarios, and you feel confident, you're going to take the test for the 4L60E. And as I mentioned here on the side, this whole process will likely take about 2 weeks to complete. So just realize as you're going through this, don't procrastinate. Don't think that you're going to get it done in 2 or 3 days, because it's not going to happen. There's a lot of content with this topic here. That's why it's worth as many points as it is. And so I'm expecting not only it to take you a little bit longer, but also you to stay busy and pace yourself and do these different exercises spread out through those 2 weeks. When you're done, the assignment Dropbox for this 4L60E, you're going to want to turn in all the worksheets that you work on, your lecture worksheet packets, your overhaul worksheet, and the diagnostic case studies. So that way it shows me you've done all the back work. Little introduction on this transmission, the 4L60E. 4 just basically means it's got 4 forward speeds. L means it's longitudinal. 60 is the relative torque capacity, and E is meaning it's electronically controlled. So this transmission hasn't really been around recently because it's been replaced by the 6L80 and the 6L90, and actually now the 8 speeds and the 10 speeds. So there's at about 2012, these things were pretty much done. And the 6L80s, which came out in about 2007, have pretty much replaced all the vehicles that had the 6L80 or the 4L60. So as they went through model changes between 2007 and 2012, the vehicles lost their 4L60Es and gained the 6L80s, and now about another 10 years later, most of those vehicles are getting either the 8-speed or the 10-speed transmissions. So this number here, like when I said 6L80, that would obviously be a 6-speed. L longitudinal. Longitudinal just basically means front and rear, or like a rear-wheel drive. The 60 is a relative torque capacity, so they've replaced them with the 6L80s or 6L90s, so they're a little bit stronger. About the weakest transmission you see in this lineup is 30. Like GM makes what's called a 4L30, and that was used in like the Cadillacs, and actually BMW used it, and it's not really designed for like a load carrying type vehicle, so they gave it the 30 designation. And then E, electronically controlled. Even on the newer units like the 6L80, they dropped the E because they're new enough to the point where they're all electronically controlled. In this case here, where we had the 4L60, as you can see on my text down here below, the 4L60E evolved from a 4L60, a non-E, which was also before that called the 700R4. And it was basically the first generation of this transmission that you're going to be working on, and it spanned from 1982 to 1992. It was non-electronically controlled. It did have electronics in it. It had a electronic torque converter clutch application, but everything else was mechanically or hydraulically controlled. Hydraulically controlled meaning they had a governor and a throttle valve. The governor was used to measure vehicle speed and create a hydraulic pressure based on that. And the throttle valve was connected to the throttle linkage, and as you gave it throttle, it changed a position of a valve in the valve body, and that changed pressure in the transmission. So the throttle valve was your load input to the transmission, and your governor was the speed input to the transmission, and between those two it could automatically shift you up and downshift you and do all that good stuff. So in 1993, they revised that transmission and threw the E on the end, made an aluminum valve body with some electronics in it, with some solenoids, but basically from the pump to the back, the design is pretty much the same. To look at it, you really can't tell the difference until you look close. Once you look close, you realize that they've improved some parts, they've changed some things. So there's really not much that's interchangeable, but at the same time, the function is, as far as mechanically, the function is the same. This is just a Wikipedia slide. I don't really know all the vehicles that have this transmission in it, so I'm trusting Wikipedia for that. You could see a variety from Saab to Isuzu. Holden is a GM company, or was. But you know, some of the latest vehicles that you would see that would have it actually have this Savannah, which is like kind of a van. That went up to 2013, but most of it was like 2012. The Colorado, and some of those were the end of their existence, so they just didn't upgrade it to a 6-speed because they knew they were just gonna quit making those vehicles altogether. But the first vehicles that had it, like, I don't know, the Cadillac Brougham, I guess they say it was 91, 92 got it, but for all practical purposes, 1993 was the first year for it. And like I said, they have the S10 marked at 1994, but the reality is 1993 is when the S10s got it. So I don't know if this is 100% accurate, but it kind of gives you an idea of how much it's been used. Now they do list a 4L65, and actually what they don't list here also is a 4L70. And it's basically the same transmission, but they beefed it up a little bit. If you remember, the relative torque capacity is that set of numbers in there. And so the 4L60 versus the 4L65, they added basically a 5-pinion planet, and they changed the 3/4 clutch. So there's all the other things that they did as well. Like the 4L70, they added an input speed sensor and so forth. But we're not really going to get into all the nitty-gritty differences between all the different transmissions. The main focus of this is to really go through and teach you how the transmission works, and so that way you can diagnose it. You know, if you're rebuilding these things for a living, or you're trying to improve upon their design, you'll do the research for that specific year range that you have to make sure that these are the things that I need to change because they're no good and they're weak. And there's companies out there like Sonex, Transgo, and they will have a lot of information on how to improve upon the design of these transmissions. Here we have the range reference chart, and this is pretty much the same chart that you'll find on page 11 of the 4L60E Technician Reference Guide that's up on D2L. And it basically shows all the clutches. We've got reverse, forward, 3/4, and overrun clutch. And these are all our input clutches. We got 2/4 and a low roller and low reverse clutch. And really the roller is a one-way clutch, kind of like this forward sprag. So the sprag and the roller are going to be devices that are mechanical, and they're going to hold in one direction and freewheel in the other direction. Whereas our input clutches, I'll just put an I there, these are going to take torque from the engine through the torque converter and deliver them to gear sets, whereas these others are holding clutches, and they are going to hold parts of the gear set to the transmission case. To look at our range reference chart, you could probably imagine the value in a range reference chart is if you've got an issue with one gear, and you can look at a range reference chart to see what happened, to see what changed. If you were good in second and now you're bad in third, you would say, well, what changed when I went from second to third? And in this case, you'd be looking at, okay, my 3/4 clutch came on, so maybe I have a problem with the 3/4 clutch. And so these are very valuable tools, is to look at a range reference chart, especially when you get to other transmissions where they don't give them the obvious names like a reverse clutch or a 3/4 clutch. Sometimes they'll just label the clutches A, B, C, D, and E. So you don't really know what they're doing by just looking at the name of it. You have to look at a range reference chart, and then you could say, okay, my E clutch is probably the problem. But here also on this range reference chart, we have the shift solenoid states. You could say they get shift solenoid A and shift solenoid B. And if you look at my shifts from first through fourth gear, A is on, both A and B are on in first. A turns off for second. They both turn off for third, and A turns back on for fourth. When we go through the electronics and the hydraulics, you'll see how they're actually controlling the shift valves using these solenoids. But so we see our solenoid states, and we see our clutch apply states by looking at this chart. A little bit more on the chart, a few things that you'll notice. One is that even when I'm in park, I have a low reverse clutch applied. And the reason why they do that is because when you shift from park, you're either going to go to reverse or drive, likely. And if you go to reverse, you already have the necessary clutch applied, and all you'd have to do is apply the reverse clutch. So that allows for a quicker engagement and possibly a smoother engagement, because they only have to concentrate on controlling the apply of one clutch. The other option is shifting it into drive. And even though the low reverse clutch is not applied in drive, you're going to find that it's holding the same part that the low roller is holding. So as this low reverse clutch releases when I shifted it into drive, it didn't really make a difference because I have a mechanical device holding it anyway. But still, all I have to do is apply one clutch, and that's the forward clutch. So that prevents delayed engagements and allows for smooth shifting. So we're going to go through all these different clutches and go through what we call a job description. The job description just basically says, what are these different devices for? What are they holding? When are they used? And we get to see a few different things that we haven't seen yet, like the band. We're using a band, we're using a sprag, and we're using a roller in this transmission. So those are three things that should be new from what we've covered up until this point. Starting with our input clutches, going from the top to the bottom. And as I mentioned earlier, I do have these parts and actually have this cutaway. So even before you when you're trying to study this transmission, you could come in and kind of handle these parts and try to get familiar with them hands-on. But the reverse clutch housing right here, it has a clutch inside it, and when that clutch applies, it actually grabs onto the hub of the input drum. The input shaft that's behind this picture on the top comes in and drives this whole aluminum hub right here. So once I apply my reverse clutch on the inside of the reverse drum and it grabs onto that input shaft or input hub, now my reverse clutch housing is going to be spinning as well. And you can see the lugs that I've got on this reverse clutch housing on the outside there. Those lugs are going to grab onto a part that drives a sun gear, a reaction sun gear. So we'll see that when we cover Powerflow. But it is an input clutch, so that way when I apply my reverse clutch, it's now going to drive turbine shaft speed, and the shell of this reverse clutch housing is going to be able to drive a sun gear. I have 3 clutches total in this input drum, and you'll see some on the next slide. But the furthest most in when you're taking it apart is the overrun clutch. And I know I'm kind of doing this in a different order, but the overrun clutch, as its name implies, what you don't see here is there's a sprag assembly inside there. And the overrun clutch, its job is to prevent that sprag from freewheeling. So the only time you'll use that is when you want engine braking or compression braking, because here's a little tidbit here, a little piece of information that you probably want to remember, that if torque is ever transferring through a one-way clutch, whether it's a roller or sprag or ratchet type, doesn't matter. If torque is having to travel through that one-way clutch to give power to the wheels, that when you take your foot off the throttle, you're going to be in your coasting, your engine's going to be allowed to idle down because that sprag will be able to freewheel. So whenever you have a roller or one-way clutch, like I said, whether it be a sprag or a roller, if torque's traveling through it, you will not have engine braking. As soon as you take your foot off the throttle, it'll allow your engine to coast down. So there are going to be times where you want engine braking. If you're towing, is a good example. If you're in hilly terrain and you're not wanting the vehicle to coast downhill faster than you want to, you can put it in a manual gear range and hold it in that gear. So what happens when you do that, you apply these things like this overrun clutch, and it drives both sides of the sprag so that way it can't freewheel. And if it can't freewheel, now I've got engine braking. So that's the purpose of this overrun clutch. Where this arrow is pointing here, erase a few of these things, there's a forward clutch in here. So this is the forward clutch right in this area. And the forward clutch is going to grab onto the forward sprag, and the forward sprag is going to, through a sun gear, drive the input gear set. So as soon as you shift this transmission into drive, the forward clutch applies. And now torque is going to be delivered through a sprag. It's going to be delivered to the input to the gear set. Like I said earlier, you can't see the sprag with this cutaway. It's in there. The forward clutch plates that we're seeing right now, those are around the outer race of the sprag. So when the clutch applies, the engine torque from my input drum, it's going to now deliver torque to the forward clutch and then to the outer race of the sprag. And we'll see the sprag coming up here. This is that sprag assembly, as I mentioned. And like I said, and if you follow this blue arrow, is located in the input drum, and the outer race of the sprag has splines on it, and that's what the friction discs grab onto. And the inner race has splines on it that grab onto the sun gear, the input sun. So what happens is when torque is transferring through this in a clockwise direction, it pushes on these sprag elements, and these sprag elements lock in the clockwise direction. And that's going to drive my inner race, which has got the sprag or the sun gear attached to it. So now so that way I can think of this as when I'm accelerating, I'm driving the sun gear through the sprag elements. So these sprag elements right here are carrying all that torque. And then when I take my foot off the throttle and the sun gear wants to continue to rotate because now the wheels are driving it, it can, because my engine could slow down while my sun gear continues to rotate in the clockwise direction, because the sprag will allow the inner race to go clockwise faster than the outer race. we'll actually see that show up here when we shift to fourth gear, because that's one of the big reasons why they have a sprag. And a lot of transmissions don't utilize one-way clutches like this, but the reason why this transmission does is because when we're first, second, and third gear, we need the forward clutch to drive that sun gear. But when this transmission shifts into fourth and we get overdrive, the sun gear is actually going to spin faster than the forward clutch. And instead of releasing the forward clutch when we shift from third to fourth, they just let it freewheel. They let it go faster because we've got that sprag in there, and it won't hurt anything. So that way they don't have to time the release of a clutch. All they have to do is bring on all they have to do is bring on the band, and we'll see that coming up. I know there's a lot described on this, so as you're watching this, please, rewatch it if you have to, or even watch it at school with some of these parts in front of you. And it helps to have these parts in your hand when you're spinning these things and trying to understand it. So let's see what I wrote down here for the forward sprag. The inner race is splined to the sun gear. Also contains that overrun hub, because that's how these overrun clutches, when it's applied, it drives the sun gear inner race, and then the forward clutches drive the sun gear outer race, so that there's no way the sprag could freewheel. And as I mentioned before, that overrun clutch is there to prevent engine braking, or to provide engine braking, to prevent engine from freewheeling. So, and I also mentioned with that sprag, when holding the sun gear in your hand, so if you had your hand underneath this picture here, because the sun gear's, this is the sun gear, you can't see it, it's sitting on a table, but so it's on the other side, but if you had that in your hand, you would see that the outer race would drive the sun gear if you tried to rotate it clockwise, and if you tried to rotate the sprag race counterclockwise, it would freewheel. And I'll show you that here in a video in a second. Lastly, we've got the first clutch that you take out, basically, or the one that you can see, is the 3/4 clutch. This is actually a pretty weak link in this transmission. The piston lives way on the inside of this drum, and it applies the 3/4 clutch through these fingers, applies up on this plate, and compresses that clutch pack assembly. And the 3/4 clutch, as its name implies, is applied in third and fourth gear, and it drives the input or front internal gear and the reaction carrier. So we've got a kind of a combined gear set where one part of the front gear set is connected to one part of the rear gear set. And so if I'm driving the front internal gear or input internal gear, I'm also driving the reaction carrier, which is the rear carrier. And so that's the purpose of this 3/4 clutch. So there's 3 clutches as a summary. There's 3 clutches in this input drum. Underdrive, I'll mark these in green. Overdrive, I don't know why I said underdrive. Overrun, forward, and 3/4. Those are our 3 clutches. And located in there as well is a forward sprag assembly. This is the reverse. Now let's look at our holding elements. These are our devices in this transmission that can hold a gear set part. And what we have is a 2/4 band. This is a device, it's like a belt that wraps around a smooth drum. You can see our reverse clutch housing, because you're like, wait a minute, this reverse clutch housing, you said that was an input component, and it was. It has the ability of driving this reaction sun gear when it's applied, but they kind of make the drum do double duty there. They're letting the drum itself be the a holding surface. So now when I apply this band, I use a device called a servo, and it locks this band around this drum. That stops the reverse housing from spinning. And if the housing's stationary, so is that sun gear, the reaction sun gear. So we have the ability of driving and holding this reaction sun gear. The reverse clutch will drive it, and the 2/4 band will hold it. The low roller is another device, and the low roller is located right here. It's shown. And these lugs that we see on the outside, they lug into the case. You're going to see that. Obviously, you're going to handle it when you overhaul the transmission. But the lug assembly, that gets lugged into the case. And what you cannot see here is there's a series of rollers on the inside of this. This allows the carrier assembly to spin in the clockwise direction all the time, but it will never let it spin in the counterclockwise direction. It's a mechanical clutch, so that means this carrier is never going to spin in the counterclockwise direction because this clutch assembly is always there. It's mechanical, it doesn't need to be applied by hydraulics or anything like that. Since the outer splines here are lugged to the case, it's a physical connection that's always there. So this rear carrier and front internal, because remember those are splined together, I mentioned that with the 3/4 clutch. The 3/4 clutch grabs onto that part, and since they're splined together it drives that. So the input internal and the reaction carrier assembly, the only direction they could spin is clockwise. They'll never be able to spin counterclockwise because of this low roller. There's also another clutch, which I don't actually have the clutch discs shown on this screen, but you can see, looking at the bottom picture here, the reaction carrier has these splines that are kind of machined into it. As you can guess, friction discs will spline into that reaction carrier. There's a piston at the bottom of the transmission case. When the piston comes up and compresses that clutch pack, it's going to lock this reaction carrier and this input internal gear to the case, and it'll prevent it from spinning in clockwise or counterclockwise. So we always have this mechanical clutch, this low roller, to prevent it from spinning counterclockwise. But if we need to prevent it from spinning clockwise, like we do in reverse gear, we'll have to apply our low reverse piston and apply this clutch. And we also apply it manual first, just for the sole sake of preventing the engine from coasting down and to provide us engine braking. As I mentioned earlier with the Sprag, that if torque ever transfers through a one-way roller clutch, if you take your foot off the throttle, it'll allow the engine speed to slow down because it'll allow the gear set to continue to rotate faster, or the wheel speed, but let the engine speed coast down. So if torque is required, in order for torque to occur, I have to have something held through a one-way clutch. And if I want engine braking, I have to bypass that. I have to prevent whatever freewheels from freewheeling. So in this case, we're looking at, like if I pull it into manual first, because I want engine braking, I'll have to apply the overrun clutch in the input drum to prevent the Sprag from freewheeling, and I'll have to apply the low reverse clutch to prevent this input internal and this reaction carrier from spinning or freewheeling. As far as our holding clutch, the servo assembly in this transmission is pretty neat. There's a lot going on here, but these are the common gear set connections. If we were to say, all right, if one's spinning, the other's spinning, and I just got done mentioning on the previous slide how there is a common connection between the input internal. Remember, anything that's on the front half of the gear set, by the way, is input. That's just the way GM calls it. So they're going to call everything on the front half input, even if it's splined to the output shaft like this one is. This is what we would call an input carrier, but it's splined to the output shaft. But I don't know who came up with that crazy idea, but it's basically everything that's on the front half of the gear set is called input. Everything on the rear half is called reaction. I can't spell well with the mouse. React. I'll just say react. So common connections, if we think of the parts of the gear set that are always connected to the output shaft, is going to be the input carrier, as we see here, and the reaction internal gear. And everything, and this gear set over here on the right side of the screen, they're commonly connected because they're splined. The input hub assembly or input drum assembly, the input internal gear assembly splines itself into the reaction carrier. So if my reaction carrier is held, so is my input internal gear. If my reaction carrier is being driven, so is my input internal, and vice versa. So those are common gear set connections. What you don't see here is the front sun and the or input sun, front sun, or the reaction sun, rear sun. Those two are independent of each other. They do not. There's no common connection with those gears. They basically live. They're the only two gears that are just by themselves. Common gear set connection. This is a diagram showing the power flow. So some people can understand power flow easily by looking at it and trying to figure out what's going on with the drums and the gears and all that. Some of them, because power flow can be difficult to understand. It's almost like electricity where you don't see it, so you have to kind of believe it. And when you're looking at these planetary gear sets, a lot of times you can't see the gears when you're spinning these parts. You're just watching a shaft on the input side move and a shaft on the output side move, so you're just kind of believing it. But this is a pictorial representation of what's going on in the gear set. This shows every clutch and what's driving what. So my input gear set is going to be on the front half, and my reaction gear set or rear gear set is going to be on the back half of the gear set. And we're looking at these common connections here. So like on the previous slide where we talked about the front carrier, rear internal gear, that's what this is showing. That's a front carrier and this is a rear internal gear. And showing both sides of it. Another common connection that we referred to on the previous slide was the input internal gear and the reaction carrier. And we could see that here. There's the input internal gear, there's a reaction carrier. So hopefully this illustration, when you first look at this, it's like, what is going on here? There's a lot of lines, but I think if you understand the drawing, then it helps you understand what's going on in this transmission. Because all these arrows coming in from the side, those are all different clutches. And all the arrows coming in from this side are input clutches. So they're the ones that are going to be driving, taking engine torque and try to drive a gear set part. And then all the clutches from that have arrows pointing up, they're going to the transmission case. So as you can maybe imagine, those are all holding clutches. So we labeled those clutches. So like if the 3/4 clutch, it's going to end up driving my input internal gear and my reaction carrier. The forward clutch through the sprag, that's why the forward clutch doesn't go directly to that input sun gear, it goes to the sprag. So the forward clutch through the sprag is going to drive the input sun gear, whereas the overrun clutch has the ability of going in and driving directly that sun gear. That way, if I have the forward clutch and overrun clutch applied at the same time, that sprag can't freewheel. Aha. If we look, we also have our reverse clutch, and that's kind of drawn a little differently. The reverse clutch comes in here and has the ability of driving my reaction sun gear, but if you also look, the 2/4 band has the ability of holding the reaction sun gear. So you can imagine those two would never be applied at the same time because you can't drive something that's held, or you can't hold something that's being driven. And then in blue, I've got my low roller clutch because it's designed to hold the reaction carrier input internal gear assembly. And so I'm going to do that in the counterclockwise direction because it's a mechanical clutch. And then I have the low reverse clutch that can hold the reaction carrier input internal gear assembly, but it'll be able to hold it in both directions. So hopefully looking at this, you'll be able to kind of get an idea of how this gear set works. And we'll go through the power flow with each gear, and like I said, this helps a lot of people understand it. We'll look at the block diagram like we have here, and then we'll also see a video of me basically going through the power flow and individually for each of these gears. In park, which is a pretty easy one because there's no torque being delivered through the gear set, but we do have a clutch applied in park. It's the low reverse clutch. The low reverse clutch is anticipating a shift into reverse, so we can go ahead and apply it. So that way all we have to do is apply the reverse clutch. So right now we have an input shaft that's spinning, or an input drum that's spinning, but none of the clutches are applied, so they're not physically driving any of these gear set parts. If you remember, in order for torque to transfer through these planetary gear sets, I either have to have something held and something input, or I have to have two parts input. And I've got something held, but I don't have any inputs, so I'm in neutral, or in this case park, because the parking pole is applied. If we shift into reverse, now what I've done is I've applied hydraulic pressure to my reverse clutch, or the reverse piston, and that applied the reverse clutch. And the reverse clutch is going to grab onto the input drum and now spin input shaft speed, or at least deliver torque from the input shaft through the reverse clutch housing to the reverse shell, the reaction sun shell, and then that finds its way to the reaction sun gear. So now, once I'm in reverse, I have a input device, or an input component, which is the reaction sun gear. Now also, because even in park I had the low reverse clutch applied, I have a held part, which is my carrier. So if I labeled these and said my carrier is held and my sun gear is input, the third part has to be output, which is my internal gear. So what I'm doing is I'm inputting the smallest gear and outputting the medium-sized gear. If you remember back when we talked about gear set rules also, that whenever you hold a carrier, reverse gear rotation occurs. So I've got clockwise rotation on my sun gear. My pinion gears are going counterclockwise, because it's an external tooth gear meshing with an external tooth gear. But this is where the this little feature occurs, is that when an external gear is driving an internal gear, same direction rotation occurs. So now my planetary pinions that are spinning counterclockwise, they're going to force my internal gear to also go counterclockwise. That's how we get reverse rotation whenever we hold a carrier. In reverse, now we shifted out of reverse, released the reverse clutch, and I shifted it into drive and first gear primarily. So now we apply the forward clutch. And the forward clutch is going to deliver torque from the turbine to the input shaft through the forward clutch. And the forward clutch, if you remember, it drives the sprag assembly. And the sprag assembly is then going to drive my input sun gear. So that's now my input component. We still have this low roller clutch, and as soon as I placed this in the drive and I started producing torque and trying to drive that sun gear, what actually ends up happening is this reaction carrier input internal gear assembly, it's going to try to rotate counterclockwise. That's just a reaction that occurs because my front carrier and rear annulus gear are being held by the drive line to the rear axle, to the wheels and all that. They're really not moving, or at least if they are rolling, they're rolling slowly. So the reaction that occurs when I start driving that forward clutch and the input sun gear, when I start driving that clockwise, it's going to want this input internal and this reaction carrier assembly to try to spin counterclockwise. If you remember, when we were talking about these parts and pieces, there's a device in there that prevents the reaction carrier and input internal gear from spinning counterclockwise, and it's the low roller. That low roller assembly is going to lock it, prevent that counterclockwise rotation. It's a mechanical clutch. It's always there. It doesn't need hydraulic apply or anything like that. So we get this, it prevents counterclockwise rotation. So this ends up being my held component. And my output is then going to be my input carrier assembly. So you can see in first gear, the smallest gear is the input, the largest gear is the output, and the medium-sized gear is held. So that gets me my best gear reduction, which is a little bit better than 3-to-1. And that's how we get first gear. In first gear, the low roller clutch. Second gear is a little more complicated because we're not using just the input side of the gear set or the reaction side of the gear set. We're using both halves of the gear set. when I shifted from first to second, all I really did was have to apply this band, this 2/4 band. And the reason why all I had to do is apply something, I didn't have to release anything, is because if you notice what's missing here, my low roller is not there anymore, because it's actually going to now, once I apply that band, this input internal gear reaction carrier assembly is going to spin clockwise, which the low roller will allow that to happen. It was being held in the counterclockwise direction, but once that band's applied, it's going to start freewheeling in the clockwise direction slowly. So how does power flow actually occur when we look at second gear? The torque is going to, we're still driving our input sun gear, so this is still the input component, but now I'm holding part of the reaction gear set. So by holding part of this reaction gear set, I actually, like if I go back and think about what was happening in first gear, what was held in first gear was my input internal gear assembly. Now what happens when I apply this the reaction sun gear and I hold the rear sun gear, that actually through the reaction carrier starts driving in a gear reduction. It starts driving my, so I'm going to X out that hold there. It's going to start driving in a gear reduction my input internal gear. I'm still going to react off of this moving input internal gear, but now what's done is it's basically caused a gear reduction between the input gear set, the input carrier. It's still going to cause rotation there, but what it's done is it's stolen some of that gear reduction that I had in first gear. So instead of being the ultimate gear reduction where I have a part that's held and a part that's input and a part that's output, I still have the part that's input and the part that's output, but my held component is actually moving now. I'm reacting off of a moving component. And that's also the reason why instead of just always saying that something's held, something's input, something's output, using the term reaction actually makes more sense. This front gear set is still doing a lot of work. It's still basically, now both gear sets are required for second gear to work, but the gear reduction and how this thing is accomplishing its second gear ratio is more of a function of this front gear set, because of this moving input internal gear is working as a reacting component. So my sun gear is driving the carrier, but it's driving it and it's reacting off of this moving input internal gear. I know it's complicated and it sounds weird and it's not as simple as some of these others. All the other gears in this transmission we could say are occurring either from an input gear set or from a reaction gear set. We can do that on every gear in this transmission except for second. But the best way to understand second is to realize that parts aren't always either held or being driven by the input. You could have parts that are moving and reacting off of a moving reaction, and that's what's happening in second. When we shift from second, in third gear, we've now released the 2/4 band and we've applied this 3/4 clutch. So this is going to be an input gear set responsibility, because you could see I am driving the input internal gear, I am driving the input sun gear, so that means this input carrier, which is connected to the output shaft, is going to have to spin the same speed. If I got two parts that are input, that means I've got the third part's going to have to go input shaft speed. So it's a pretty easy gear to understand. So in first gear we use the input half of the gear set, and in second we use both the input and reaction. In third we're using the input half of the gear set. In fourth you're going to see now we're going to use the reaction half of the gear set. In third gear the 3/4 clutch grabs. In fourth gear I still have my forward clutch applied, although it's ineffective. It's not doing anything because my sprag assembly is going to allow the sun gear to spin faster than the input drum. That's part of the reason why they put the sprag assembly in there, is so they wouldn't have to worry about the shift from third to fourth. They could just apply one device, the 2/4 band, and let the sprag freewheel. That allows for a smooth shift. So we still have our 3/4 clutch applied, and the 3/4 clutch is still driving my input internal gear, but it's also driving my reaction carrier because they're a common connection, and they're always, if one's spinning, the other's spinning. What I've done now when I shifted from third to fourth is I reapplied my band. That's why it's called the 2/4 band. It's applied in second and fourth. So once I reapply that band, I've stopped the sun gear from spinning. So the reaction sun gear is held. My reaction carrier is input. So my reaction internal gear is output. And like I said, unlike second, we're just using now this reaction gear set, and unlike second, you have only one half of the gear set being used, and you actually have a part that's input, a part that's held, and a part that's output. So also, if you remember some gear set rules, that if you ever input a carrier, since it is the largest gear, you know you're going to get overdrive. But in this case, you're getting like the minimum overdrive because you're inputting the largest gear and you're outputting the medium-sized gear, which is the internal gear. In fourth gear, I still have manual low is just like normal first gear, except I apply the low reverse clutch. The reason why I do that is because I want, and also I guess I need to throw in, we apply the overrun clutch. Because the idea here is that if I'm in manual low and I take my foot off of the accelerator pedal, that I want the transmission and the drive line to help slow the vehicle down. I want to get compression braking or engine braking. And by having the overrun clutch and the low reverse clutch, I'm able to bypass those rollers. And I don't even know if I like the term bypass because you're not really going around them, but what you're doing is you're preventing them from freewheeling. So the overrun clutch, for example, is going to prevent the input shaft from slowing down and allowing the sun gear or the gear set to continue to rotate at driveline speed. It's going to keep the gear set physically connected to the input drum, so there won't be any freewheeling. And the low reverse clutch is going to prevent the low roller or the reaction carrier input internal gear that will normally be held in the counterclockwise direction. It's also preventing it from rotating in the clockwise direction. And you need to do that for low range. When you're driving this vehicle in manual low, you actually, or in first gear, let's say if you're driving this vehicle in first gear, when you're accelerating, torque is going through the sprag into the sun gear, and the carrier is trying to rotate counterclockwise, it's being prevented by the roller, so you're able to accelerate. But you take your foot off the throttle, you're going to let the engine spin down while the output gear set continue to rotate, and what's going to end up happening is you're going to be freewheeling these rollers and sprags. So by applying those clutches, I'm not allowing that freewheeling to occur, and it will give us compression braking or engine braking, which we want, manual low. Powerflow in manual low is just